Hi folks, CEO speaking again. Last time I presented you an application, an example about the function AND, just the function. How the function AND is defined, what does it do? So you have an application with two contacts and they have to be both on one and the other in order to have an output energized. So now we are going to do the math behind that function. So let's start it. We're going to call this the AND gate. Remember what a gate is when you put a function inside an integrated circuit, it's going to be this one, and you make it working. I'm using this paper sheet to remind you the pattern we use for all the basic gates. So A, the symbol. What symbol is used by technicians and engineers when describing this function in an electronic diagram? It's going to be this one. It's something like a half circle, like this. The simplest version only contains two inputs. We have to give them names. We're going to use letters A, B. And you have here the output. You can give it any letter you want. But this is the output of the function AND. And this is the symbol for the function AND with two inputs. Of course, you may have another one with 1, 2, 3 inputs if you want. And the output here. You may have another one with 1, 2, 3, 4 inputs, A, B, C, D, and the output. And you can have another one with 8 inputs if you want, or even more. The packages, they don't contain more than 8 inputs, but you can combine 2 or 3 packages like that to have huge functions. So this is the symbol used on the diagram. So when you see that symbol, is what? Is an AND gate. B. What is the formula or the math? What the function does? Apparently that's very simple. So the output is what we call a logic multiplication. A times B. Before seeing how this one is working, I'm going to remind you here, reminder. It won't take long. Using, like the last time, the relay ladder diagram. Remember the two contacts in parallel for the OR A and B, the contacts. For the OR gate, either of these are on, the output is energized. So this is the output. But today we're going to do this one, where the two inputs are not in parallel like before, they are in series. So in order to get energy for the output, where this is the positive voltage and this is the negative one, the positive has to reach this left side of the output. So then if you have two switches, A and B, you have to have A and B together on in order to get energy for the output. So this is the function AND. How do we put it mathematically? We build what we call here C, the truth table. So there are two versions of the truth table. I'm going to draw them here. First column is the input A, or the switch A. Second column is the input B, or the switch B. And here is the output. And for this table here, we have to make all the combinations between the inputs A and B. This is why it's called the truth table, because it's telling all the truth about the function. And then we are going to convert the results we measure into the second version of that table here, where instead of having voltages we measure, we are converting them in logic state. So this is going to be called the logic table. So it's also the truth table, but it's the logic one, where here is the input A, here is the input B, and here is the output. So let's do this. Here I have a little project for you. And as you can see, if I press one button, the light goes on. I press the other button, the light goes on, and I can put it off anytime. And we are going to follow what happens to the output when these two inputs, two switches, they go on and they are monitored by lights. So I'm going to put also on a multimeter, and we are going to measure the voltage just to see what happens. Okay? So here, initially, when both inputs are off, we measure here what I can see. 0.11 volts. I write it down. I don't judge, I'm just writing the voltages. 0.11. B is right here. So what do I read? Similar voltage 0.11. What the output is? 0.10. All the measurements are in volts, okay? But then I'm going to press this button. Obviously, this input is going to go on. It's 3.5 volts. 3.5 volts. Second input is still 0.11. What about the output? As you can see, the light is off, and the output is showing something around 0.09 volt. Okay, almost the same as before. Now I'm putting the other input on, and I measure. 0.11 volts the first input, 3.5 the second input, and the output is still off, as you can see. So is 0.09. But when I have both buttons pressed, the first and the second, then the output goes on. So now we measure 3.5, second input, 3.5, and the output 3.5. Now we don't need a multimeter anymore. We convert this table into the logic one with zeros and ones, the binary. Remember, for the inputs, when they are lower than 0.8 volts, they are zero logic. So the first position, zero logic both, and the output is zero. Second situation, this is 1, this is 0. The output is still 0. Third situation, 0 logic, 1 logic. The output is still 0. And the last line here, 1 logic, 1 logic, 1 logic. Now let's check the formula before. It should be a multiplication. This is one of the rare logic operations which is identical to the arithmetical one you do on your pocket calculator. So here, 0 times 0 is 0. Perfect. 1 times 0 or 0 times 1, they are both zeros. And only when both inputs are 1, 1 times 1 is a 1. So we can check that the truth table we obtained, the logic table, it's exactly following the math, the formula for the AND gate. So far so good? Let's go for D. For D, we have here what we call the timing chart. That's exactly the same pattern I used before for the function OR. So the timing chart. What is the timing chart about? We imagine here a picture, actually a sequence of 3 pictures, the input A, the input B, and the output, as you could see them theoretically on an oscilloscope on the screen. On the right side is the time, everything happens in time, and on the vertical here is the voltage. So here, for the voltage, what we're going to do is this. I'm going to keep this input like in 1 up to here, and then I'm going to drop it in 0. And the second input, I'm going to do this. I'm going to hold it in 0 up to here. I'm going to hold it 1 for a while, and then I'm going to drop it back in 0. Now remember, how are we doing this? To figure out what the output responds to this random combination of inputs. Anytime any input is switching from 0 to 1 or 1 to 0, we drop a vertical line. Like here is the first one, here is the second one, and here is the third one. And for each interval of time, like from here to here, I'm going to write for each input what is the value. Here is a 1 logic, because this line is high with respect of the ground. Here is still a 1 logic, here is a 0, and here is a 0. Second one, here I have a 0, here I have a 1 from here to here. From here to here I have another 1, and then from here to the end I have a 0. So now the output should respond exactly like in the truth table. So if at least one of the inputs is a 0, 0 times anything else is a 0. So I'm going to have here a 0, here I'm going to have a 0, and here I'm going to have another 0. Only when both inputs are 1, 1 times 1 is a 1. So that's how the output responds. The last step is to build here the timing chart for the output. When it is 0 is down, close to the bottom line. When it is 1 is up, close to the 5 volts. And this is how the output responds to that. So these two, the timing chart and the truth table, they are equivalent. And later on, when the circuits are becoming a bit more complicated, I'm going to tell you when this one is used and when this one is rather used instead of the logic table. But right now, both of them are explaining beautifully the functioning of the gate. In this situation, the AND gate. So this is actually the functioning of the AND gate. At the point E, I'm going to put here packages. Are there any packages containing this gate implemented inside? Of course they are. Example, 7408. So when you see that number here, 08, this is identifying the AND gate in TTL. Why TTL? Because of 74, now you know. And there are variations of this. It may be 74LS, 74ALS, 74HC, 74HCT. And in CMOS, in the first generation of the CMOS, I'm going to give you the equivalent one, is 4081. This is also AND gate, like this one. However, not only the voltages may be different for the two kind of packages, as in another video, but also the packages are not interchangeable because the way the gates are arranged inside is not the same. How do I know that? Give me a second, and I'm picking up a paper you're going to find on Google Drive. And here, this layout corresponds for the versions I wrote right here. The 7408, LS, ALS, HC, HCT. But the one in the bottom corresponds for 4081, regardless if it's a standard one made by RCA, Fairchild, Intel, whoever. And this one is for Motorola. Remember, Motorola puts, let me highlight it. It puts the number 1, like they were the number 1 back in time, before the actual code, which is still 4081. The letter B at the end just means is a second version, better protected against the static electricity. We're going to talk about that a bit later. However, the code is still 4081. Okay, so for the packages, here you only have 2 examples, and here you have a more expanded list, but the list is not exhaustive. There are other packages containing the AND gates, okay, with 3 inputs or even 4 inputs, but these ones are typical ones with 2 input each. If you can take a look, in the TTL package, this gate here I put my finger on is in the same position as the one in the CMOS. And the same about the one in the top in the same position, but the other 2 ones on the right side, as they are arranged here, they are opposite way, reversed arranged here. So this is why the packages are not interchangeable. So you have to be very careful when you use this one and that one, because even if both perform the same function, the packages cannot be replaced one by the other one. Okay? So this having been said, this was the function AND. So prepare for the next one and more complicated things about Boolean logic. Thank you very much for watching. See you next time. Bye-bye.